binary codes of distance about half. That's what we did the study. So looking at 0, 1 alphabet codes. And we're looking at rate versus distance. I will just tell you a little bit about how this graph looks, and then we'll focus on delta about half. Focus on delta being half minus epsilon. And that's a very interesting regime in particular. Okay, so here is delta. Here, that goes from 0 to 1. This is the relative distance of the codes with and rate, which goes from 0 to 1. And good. And we're always in the asymptotic setting where n is going to infinity, and we want to know what kind of codes can exist. And we already saw the volume packing bound, which says that rate is always at most 1 minus entropy of delta over 2. That's the behavior at the end. Where h is this binary entropy function. I didn't define what it was. I said it wasn't important. It still isn't important, but yeah, that's what it is. Then there was the existence result, greedy existence, greedy or / random. Existence. This is called. I should tell you this word. This is called the Gilbert-Varlamov bound. Which says that you can have R being at least 1 minus entropy of delta. And what this translates to on this graph is two curves, whatever h is. I mean, the definition of h is basically this line which I'm going to draw. It looks like this. There are no codes above this. And at half, there are codes like this. And good. So this is the zone where we know codes exist. We don't know in here, and right, and there are no codes here. And so people have improved the volume packing bound. So an early result called the Plotkin bound showed that actually you cannot have codes above this line, showing that half is actually the critical value of delta for which positive rate codes do not exist beyond that. So this is just a fact. This is the Plotkin bound. Oh yeah, so the Plotkin bound. The main message is that for delta greater than half, R must be 0. It's not saying that the code has size 0. This is asymptotic, so R is little o1. That's what. And good. And then, and this gives some asymptotic behavior for R versus delta when I draw the straight line, it gives some asymptotic behavior for R versus delta in the regime of delta being half minus epsilon, but it's not the same as this. This has slope 0. And this does not have slope 0, so it wasn't even the right asymptotic behavior. And so what we want to do is that in this lecture is to investigate this asymptotic behavior, and we'll find approximately what the right answer is for this. Good. And then I will talk about the question of, so it's a very important question to get codes that achieve this explicitly. And this was open for a very, very long time. And so in 2018, Unknown had a breakthrough which basically gets the right asymptotic over here. So I won't have time to get into it, but I will give some glimpses of how that's done. Okay, so what is the asymptotic over here of the Gilbert-Varlamov existence result? So this may require me to understand what h of delta is. I don't want to understand it, so I will just prove it in a slightly different way. So fix delta equal to half minus epsilon. And let's show that, let us take a random linear code of dimension Rn. So this is going to be sitting inside f2 to the n. And let's ask what's the problem, and let's set R so that the code has distance delta, has relative distance delta. That's what we plan to do. So so let's pick the random linear code. Let me also call k equals Rn. So we've picked, let's say, v1 up to vk in f2 to the n uniformly. And then we look at the span of v1 up to vk. So consider the span. What's the span? I will tell you what it is. 0, v1, v2. There are lots of things. v1 plus v7 plus v9. Dot, dot, dot. And I'm interested in the event that I want all these strings to have the number of ones being at least delta. That's what the event of this code having distance at least delta is. So we want, what's the probability that for all s other than 0, non-empty, s contained in 1 to 3 up to k, we have sum over all I in s, vi equals, lies in the ball of radius delta around 0. What's the probability of this? This is what we're interested in. So what's the distribution of v1? Uniformly at random. What's the chance that it lies in this ball? Ball of radius, the volume of the ball divided by 2 to the n. Same for v2. What about here? The distribution of this, uniformly random. The probability that it lies inside the ball, again, exactly the same thing. So by the union bound over all these vectors, this is at most, there exists. Oh no, there's the probability that for all s, I mean, I just succinctly captured all these vectors and wrote. Yeah, good, okay, yeah. But the for all is okay. Yes, so the probability that none of them lie inside this is, right, so I'm union bounding, but oh yes, I see. I should have done it, there exists. You're right. Okay, so but then I was right there. Huh? There exists S such that this is in V of 0 delta. This is the bad event. I want to bound the probability of this bad event. For each one of the combinations in there, the probability of it lying in there is at most volume of the ball divided by 2 to the n, and there are 2 to the k such things. So it's at most 2 to the k times the size of the ball of 0 delta over 2 to the n. And what is, and this is exactly the same Gilbert-Rashama bound that we proved before. The greedy bound. And right, and what is the size of the ball of radius delta around 0 divided by 2 to the n? This is the fraction of 0, 1 strings which have less than half minus epsilon ones. And we know how to understand this. This is Chernoff bounds, right? This is at most e to the minus epsilon square, omega epsilon square, because delta is half minus epsilon. This is exactly Chernoff bounds, and we already know this. So if you opened it up with the asymptotics of entropy, you would get the exact leading constant, but for now, I'm going to be happy with this. And so this tells us that we can take k equals omega of epsilon square n. That's how big you can take k. And so that means that r at least omega of epsilon square is possible in the regime of delta being half minus epsilon. Okay, so that's how the curve looks around half. It is quadratic. Okay, so slope is 0. And yeah, in fact, it's quadratic. And the question is this tight? And this was not known for many years, and people studied this like anything, but yeah, the first time it was proved was by the linear programming bound, which used some orthogonal polynomials and some sophisticated things. It's all related to Fourier analysis on the Boolean cube. And they showed, yeah, so the LP bound shows that, and this is from the 70s by MRRW, McLeish, Rodimich, Rumsey, and Welch. They showed that R is always at most in the regime of delta being half minus epsilon, epsilon square log 1 over epsilon. And they also got it with the exact constant, but I will write this. But it was already, I mean, even getting the this kind of behavior, even without the constant, was only the first done by the LP bound. Okay, so yeah, so what I'm going to do now is I'm going to prove this. And it's not going to use the LP bound. Of course, it will not be as good as the LP bound, but we will not get the exact constant here, and we will not get the same behavior, but yeah. And this is a proof by Alon. He has a really nice paper called Perturbed Identity Matrices Have High Rank. Because identity matrices have high rank, even perturbed identity matrices have high rank, and applications of that fact. And there are many, many nice applications of that fact. So one of the proofs from there is this, but I'm going to take that proof, and it's actually very, very nice. But in our setting of linear codes, it comes out even nicer. And yes, it comes out even nicer, and it is actually a statement about random walks and expander graphs. So after we do this translation of Alon's proof, we will see actually that it's a proof that involves words that we have been using all week. Okay. So there's some catches, and they can be removed, but I need to do this. So I'm going to so first we'll assume. So we have a code, right? So we have a code C of distance delta is half minus epsilon. And we're going to assume actually something more. We'll assume that actually it's not just distance half minus epsilon, it's bias epsilon. Okay? That C is epsilon biased. What does biased mean? It means that all non-zero words, non-zero, have weight between half plus minus epsilon. Non-zero X in the code have number of ones in half minus epsilon n to half plus epsilon. Our proof of existence showed that. Right? When we use the Chernoff bound to bound, yeah, I mean, actually, we just, if we want to rule out strings of weight less than delta or greater than 1 minus delta, it's the exact same Chernoff bound that did it. So this, yeah, so I mean, I'm not disappointing you too much. But let me also say that there is a way of modifying this proof to also work for distance, but I won't do that now. It's just a little technical. Yeah. Delta is the relative distance. Yeah, I often say distance for relative distance. Okay. So this is one catch, and the second is this is only going to work for linear codes, and assume C is linear. And yeah, so there is some variant of this, the Alon's original variant that works for general codes. But then if we did the original one, then there won't be a connection to expanders, and yeah, what's the point? So this is linear, and the proof becomes much easier actually in this linear case. So there's some benefit to taking this assumption. So this is our setting. Questions about this? And now we're going to show that if you have a code which is epsilon biased and linear, then its rate must be at most epsilon square log 1 over epsilon. Okay, and so to do this, I'm going to set up, so it's a linear code. I'm going to set up an expander graph that captures the fact that this linear code has good distance or it has good bias. So the bias of the code will translate into the distance of this, the bias of the code will translate into the expansion of this graph. Okay, so this is, so first let's do something. So let G, this is going to be the generator matrix of my code. I'm going to take V1, V2, up to Vk. This is a basis. Oh no, I don't want to call this V1s. Oh, I call them V1s there. Okay, these are V1s, fine. This be such that V1 up to Vk is a basis for C. And I'm going to take the same matrix and, okay, I'm erasing on top, but I'm going to look at its columns, U1, U2, UN. Then the UIs are elements of F2 to the K. Right? This was a K by N matrix. The rows of it span the code, and I'm going to look at the columns. These UIs are in F2 to the K. And what's their property? The property of UIs, what I know is if you take any linear combination of the rows, you get a vector which is about 50-50 balanced, half minus epsilon. So that's the same as for any vector x in F2 to the K, that's the linear combination I'm going to take. X dot U1, X dot U2, etc. till X dot UN, these bits are about 50-50 balanced. And we know that for all x in F2 to the K, so let me say we know. So by epsilon bias, for all x in F2 to the K non-zero, the probability that this over I going from 1 up to n, x inner product ui equals 1 lies in half minus epsilon, half plus epsilon. This captured all our assumptions already. It's a linear code and it's balanced, biased. Okay, questions about this? It's an interesting collection of vectors. There are n of them. And it's good to remember that the number of them is n, which is order of k. We're in that setting. So it's not too many vectors in F2 to the k, just about 20k maybe. No, for all x, we know that half the UIs are orthogonal and half are not orthogonal, something like that. About. Correct, right. If the U1 up to UN are behaving like all of F2 to the K. If the collection U1 up to UN was the collection of all elements of F2 to the K, then that would be true with epsilon being 0. Okay. So here is our graph. This is a Cayley graph. Have we seen the word Cayley graph yet? We've not seen the word Cayley graph yet, but so I'll tell you what it is. So this is going to be the Cayley graph. So I'll tell you by instantiating F2 to the K with the set S, which is S, I'm going to call, I shouldn't write there, where S is U1 up to UN. And what is this graph? This is the vertex set. Vertices and we join x to y, join x to x plus ui for each I. Every element x in f2 to the k is joined to f2 to the k plus u1, f2 to the k plus u2, and so on up to f2 to the k plus un. So the elements of the vertices of this graph are all of f2 to the k, and we have joined certain pairs x plus u1, x plus u2, dot dot dot, x plus u1. And since u1 plus u1 is 0, so if you go to that vertex and add u1 to it, you get back here. This is an undirected graph. It is n regular. Let's say something there. N regular, undirected, 2 to the k vertices. Do we understand the graph? For every x, so for all x in f2 to the k. So every vertex which is an element of f2 to the k is joined to that itself plus these n other vertices, n other vectors u1 up to u. So that's the graph. It seems a bit, I mean, we should feel a little nervous that, oh, we chose a particular basis and we're doing things based on this particular basis. But now yeah, but the shape of the graph doesn't really depend on the choice of that basis. This is, if you had renamed if you had chosen a different set of rows to be a basis for your code, you would get a graph that's isomorphic. Okay. So how does the distance of the code translate into this graph? Yeah, so the distance comes from eigenvalues. And how? I'm going to just guess the eigenvalues and the eigenvectors. But after I guess it, you'll see that it's very natural. And so let's first see what the action. Let's take the adjacency matrix of this graph and see what its action is on functions. So take f from f2 to the k to reals or complexes. Yes, complexes. And what is let A be the adjacency matrix of G. Then what is AF? AF at X is sum over all I going from 1 up to n, f of x plus ui. That's the definition of the graph. It sums up the value of f. So AF is another function, right? F is a function, AF is a function, and on f2 to the k, and AF's value at a vertex x is the sum of the values of f at the neighbors of x. Okay, so now I'm going to tell you the guessed eigenvector. I'm going to guess all the eigenvectors in one shot. These are going to be the Fourier characters of f2 to the k. So if you've not seen what it means, if you haven't, has everyone seen Fourier characters? Okay, so I see 3 people have seen Fourier characters, and the rest were shy. Fine. So I will say what it is. It's I'm giving the explicit definition, but so psi I define so for A in f2 to the k. So this is a really basic and important thing to know about when you're studying 0, 1 to the k. So you may as well know what it is. So for A in f2 to the k, we define a particular function psi A from f2 to the k to reals or complexes, yes, reals, by psi A of x equals -1 to the inner product of A with x. And where does it come from? Yeah, it comes from somewhere, but yeah, maybe, yeah. Maybe you're reassured to know that this isn't unique to F2 to the K. For any finite abelian group, there's an analog of this. So you don't know where this is coming from. You actually don't know where lots of things are coming from, but you can get solace in the fact that they're all related. Okay, and so psi A is this is inner product is you take an F2 inner product and you're taking -1 to that power. It's okay because F2 is you only the parity up here matters, and yeah, okay. So this is psi A, and I want to say psi A is an eigenvector of A, the matrix A. All the psi, there are 2 to the K of these psi A's, and these are going to be all the eigenvectors of A. So let's see what A psi A of X equals. This is equal to sum over all I going from 1 to n psi A of X plus ui. And now the clever choice of psi A is going to play a role. This is sum over all I going from 1 to n -1 to the X plus ui inner product A. This is -1 to the X inner product A times -1 to the ui inner product A. And this is a common factor, so I can take it out. And this is psi A of X times sum over all I psi A. I could say psi A, but I'm writing -1 to the ui inner product A. So A psi A of X is psi A of X times some constant that doesn't depend on X. So it is an eigenvector. In general, eigenvectors of Cayley graphs of finite abelian groups are their characters, where characters are functions like this, which have this homomorphism property that psi A of X plus ui is psi A of X times psi A of ui. And this gives you all of them. Okay, so we got it. We got the eigenvectors. What's the eigenvalue corresponding to the eigenvector A? Pardon? Right, it is this quantity here, which is -1 to the inner product of ui with A. We already saw that ui inner product A for any A which is non-zero is about half of them are zeros and half of them are ones. So when you do that with a -1, it mostly cancels out. So this whole thing is about 2 epsilon n. Right. So we got our eigenvalues too. And it was exactly the bias that gave it to us. If you just assume distance, then you'll get the probability that x ui equals 1 is at most half plus epsilon. So you'll still get an upper bound on the eigenvalue. So it is actually an expander, either an absolute eigenvalue expander or a one-sided expander. But you get an expander. Distance gives expansion. Epsilon bias gives two-sided expansion. I mean, this two-sided spectral expansion. So the eigenvalues of psi A is sum over all I -1 to the A ui, which is in minus epsilon n to plus epsilon. The top eigenvalue is n, that's the degree as expected, and all the rest are epsilon fraction low. So we got it exactly. Okay. Good. So now we have an expander. It's a spectral expander, so the eigenvalues are small. What do you do? What are the things you can do with an expander? Well, you can apply the expander mixing lemma and study edges between sets. You can take random walks on them. You can do all kinds of things. We're going to take random walks on this graph. we're going to take random walks, and it will reveal some information about the graph. At the end, we want to show that n is big, right? That's a lower bound on the rate. We want to show that actually the degree is big. If you want the eigenvalue so small, it must be with big degree. That's the kind of statement we want to show. Questions? Anyone? Yeah, so we want to show the rate is small, which is the same as n is big. Or if you want, if you have a Cayley graph of f2 to the k, which has which has degree n and has eigenvalues at most epsilon in absolute value, then we want to show that n must be big. It cannot be too small. Okay. So we're going to do the following process. So here's a process. Pick x0, a vertex in f2 to the k, uniformly at random. And then take a random walk on the graph on G, x0, x1, all the way up to x 2t. Some even number of steps. There's some reason for that. We will take a random walk on this graph. We know that random walks will mix well. Yeah, so let me say what the high level idea of the proof is. So first we did some translation into the Cayley graph. Now we have a spectral bound on, we have a bound on the eigenvalues of this graph. So it can tell us things like a random walks mix well. So we'll take a random walk of some kind and it will mix well. On the other hand, random walks are not able to go too we will see that random walks cannot spread too much in this graph. And these two things together will give us some tension. So we take a random walk of 2t steps and we look at the event. What's the probability that x0 equals x2t? This is we start at random vertex and it depends on the t, yes. So it will be, we'll write our expression in terms of t. We start at random vertex. Good. So if I take the normalized adjacency matrix and raise it to the power 2t, that is the transition matrix for 2t steps of the random walk. And the chance of starting at a vertex and ending at that same vertex, to get it, you do trace. But that summed it up. Actually, I want I picked a vertex uniformly at random, so it's actually 1 over 2 to the k times. So the chance of a random walk, a random walk started at random vertex coming back to where it started is this, which we can now estimate using the eigenvalues. This is 1 over 2 to the k times the eigenvalues of a tilde are eigenvalues of a divided by n. So that's so it's 1 and a whole bunch of less than epsilons. And then when you take it to the power 2t, when you take it to the power 2t, all the eigenvalues got raised to the power 2t. And then, so it is 1 plus sum overall, so it's 1 plus, in fact, it's plus, right? So it's at most 1 plus epsilon to the 2t times 2 to the k minus 1. Which I'm going to bring the 2 to the k in. So this is at most, and the minus 1 I don't care for. So it's going to be 1 over 2 to the k plus 1 over 2 to the k times epsilon to the 2t. This should be a factor of 1 by n. No, because it was epsilon n were the eigenvalues, and I divided by n. So it's already epsilon. Okay, and just let's understand what this means. I brought the 2 to the k in here. Ah, correct. Good, good. Oh, yes, yes. And this would have caused trouble also. Yeah, right. Thanks. Okay. It's 1 over 2 to the k. This is the collision probability. I mean, we have, yeah. Of a completely random sample, right? And this is some extra error that came on top. Okay, so this is, so this was the one way of analyzing this process, the probability of x0 being xt, x2t. There's another way of getting a random walk on G that starts and ends at the same vertex. We'll take a walk of length t. We'll take 2 walks of length t. And so there's the first walk from x0 up to xt, and there's the walk from xt back to x2t. So does that second walk come back and hit x0? That's another thing. So how do I do this? Probability that x0 equals x2t. This is the probability that x0 up to xt. So we sample 2 walks. That for 2 walks, x0 up to xt and xt plus 1 up to x2t. Right, so there's the returning walk, which I can now reverse. Both have x0 equals x2t. I mean, they satisfy x0 equals x2t as such. And so now I want to notice that xt plus 1 up to x2t, you could have also done start at x2t and walk until you hit some vertex. So it's the same as 2 different random walks start and end at the same vertex. So this is the probability that 2 independent walks I see. Maybe there's a given somewhere. Start and end at the same vertices. No, maybe 2 independent walks starting at x0. End at the same vertex. Yes, good. So let me say that better. Instead of starting sampling x0 up to x2t, I start sampling x0 and this also as x0. And I start the reverse walk also, I've sampled both of them, and that after t steps, they end up at the same point. And if they do, then I got a hit for, I got a way of them coming all the way back. So x0 is picked uniformly at random, and then I start 2 walks of length t, and I ask what's the probability that they end at the same vertex. And that is exact same thing. Okay, so what's the probability that they end at the same vertex? So one thing, so let's notice that, so this is the collision probability of some distribution. It's actually the average collision probability over all choices of x0. But the collision probability of distribution, you have taken 2 samples from a distribution. The chance that those 2 samples are both equal to each other is at most 1 over the, no, it's at least 1 over the support of the distribution. So this is at least 1 over the the number of vertices. So it's actually the average, right? So it's at least expected over the choice of x0, the number of vertices reachable from x0. And the answer is the same for all x0, so I won't need to. How many vertices are we reachable from x0 in t steps? How many vertices are reachable from a single vertex in t steps? That's the combinatorial property of this Cayley graph that we need to study. A degree raised to n. Okay, so I don't know if I have enough time to do it in a fail. So that is true, but that is an upper bound that's a bit lossy. The reason is, if I take step u1, u2, u3, u1 again, then it's as though I never took u1 at all, because this is an f2 and we're adding. So okay, so in light of that, what is the number of? N plus d choose d. Yes, so good. Right. So you never take an edge twice. Also, the order doesn't matter. Right? D to the and degree to the power t would have is even more lossy because the order doesn't matter. So the order, degree to the power t assumes that v1 and then v2 is different from v2 and then v1, but actually everything is the same. So u1 and u2 is the same as u2 and u1. This happens to be the same, but if we counted it degree to the power t, it would have not taken advantage of that. So we want to take advantage of that. So the number of vertices reachable is actually small. It's, I will be loser even, I will say, it's at most the ball of radius t in f2 to the n. In 0, 1 to the n, that's the volume of the ball of radius t. It's like we have these n different coordinates we can play with. The n different coordinates are not coordinates, they're actually vectors u1 up to un, and I have to choose up to t of them and add them up. So this is at least 1 over, because the answer is the same for all x0, the ball of around 0 of radius, no, in n dimensions, right? The ball in n dimensions around 0 of radius t, which, yeah, so this is about, yeah, there's n, yeah, n choose, let me say 1 over n choose t. Let me say this, please. Okay. So now we have something to compare. This probability is at most 1 over 2 to the k plus epsilon to the 2t, and it's at least 1 over n choose t. So I'm going to simplify this and set t to something nice. So the t that we'll finally set is going to be humongous, about k, yeah, almost k. So 1 over n choose t is at least, at most, 1 over 2 to the k plus epsilon to the 2t. And so that means n choose t, n choose t is at least 1 over, okay, that makes it a bit messy. Let me take roots beforehand. Okay, so n over n choose t, this is like n over t whole to the t, right? So this means t over en, to the power n to the power t. So this, I'm just doing some approximation. Is at most 1 over 2 to the k plus epsilon to the 2t. So the good setting turns out to be make epsilon to the 2t equal 1 over 2 to the k, so that these two terms are comparable. So I will set them equal. So set t such that 1 over 2 to the k equals epsilon to the 2t. So that's the same as t log 1 over epsilon equals k. So t equals k over log 1 over epsilon. When I've set that, this whole thing is like 2 times epsilon to the 2t. So t over en whole to the t is at most 2 times epsilon to the 2t. And then take t'th roots of this, and we get n is at least, I brought the n here, t over e times 1 over epsilon squared. Right. E is just E, right? So that's at least omega. And T is K over log 1 over epsilon. So that's where the K is coming from. The K is, the 1 over epsilon was already waiting for us, but the K came later. And this is K over epsilon squared log 1 over epsilon. So it just works out. So maybe it's instructive to know what length walks we took. We took walks of length almost K over log 1 over epsilon. That's the kind of. Okay, so that's it. We saw the proof of epsilon squared log 1 over epsilon. To do it with distance, there's some tiny trick that one has to do when analyzing this expression. The problem is there can be some negative terms which, when you raise to the power 2t, become humongously positive. And we know that all the eigenvalues are between epsilon and -1. So when you raise to the power 2t, some of them can become very positive, but then you have to separately bound those, which, okay, turns out not to be so difficult. Okay, questions about this? The eigenvalues tell you the random walks spread well, but this graph does not have enough degree, or the nature of the graph being commutative did not let you spread so fast. And yeah. So why is it at least 1 over this? Or how did we estimate this? Okay, so for any distribution supported on a set of size k, if you take 2 random samples from the distribution and ask what's the probability that they're equal, it is at least 1 over k. And this is Cauchy-Schwarz. Okay, good. So let me also, so now we're in the half minus epsilon zone. So I'll tell you about the explicit constructions of these codes. This, yeah. Oh no, that is the non-determinism of all of life, right? Yeah, I mean, right. Yeah. It's very, it is the clever proof that, I mean, it was only discovered many years later. Yeah. But I mean, the moral is sometimes it helps to introduce an experiment of your own on this thing and study probabilities around it. Maybe it will reveal something. Right. but for one for which we had two different ways of understanding. That's, I guess, the key. Okay, so explicit constructions. Of codes at delta equals half minus epsilon. Okay, so yeah, so for a long, yeah, good. So we know that the optimal codes, optimal rate is about, O tilde of 1 over O tilde of epsilon square. And for a very long time, the best known are with explicit, for an explicit code. Yeah, till 2018 was R being O of epsilon cube. And these are produced by taking codes over large alphabets and concatenating them down. And when you concatenate it down, you concatenate with a code that is the best possible. Right. So you start with the Reed-Solomon code with rate epsilon, with the distance epsilon and rate 1 minus epsilon, and then you concatenate it down with a code on a smaller instance. That's what concatenation lets you do. A code on a smaller instance with the optimal rate distance trade-off, like this. And that you can hope to get by brute force searching for the code. And that gives you ultimately this kind of behavior. Right. But then in 2018, Amnon showed that he gave, this is in 18, he gave an explicit construction code in this setting with R being epsilon or omega, I should say, omega of epsilon to the 2 plus little o1. I mean, so it is epsilon squared times some polylog epsilon. And right. And it was based on expanders and in a really beautiful and very elegant way. So I'm not going to be able to say much about this, but yes. Oh, yes, right. That's right. Yeah. So these codes were explicit, and it was a construction of a code with provable distance half minus epsilon and this rate. But then you have the code, but then maybe you also want to decode it, and decoding it up to half its minimum distance was not known directly from there. And then it took many ideas. So Madhur and students and co-authors et al. Many of whom are coming next week, developed a whole bunch of machinery to decode these codes and also decode many other codes, and we'll see many of these results next week too. Saying that decodable in poly n and even near linear time, I believe now, right? So poly n and now n to the 1 plus little 1 time. So now the problem of getting these codes is, I mean, the main questions are solved. You got the codes, and we know how to decode them super fast. And okay, so I'm not able to say much about the constructions. I have, I guess, 5 minutes. But so I'll give one mild, high-level outline of how the shape of these constructions go. Yeah, so this is the example that Amnon also mentions in his paper. So this is an idea of Rosenman and Wigderson, and it's related to things like the zigzag product and de-randomized squaring of graphs and a bunch of other ideas that came up in pseudo-randomness. It is a transformation that takes an epsilon biased code and makes it an even better biased code. So it improves the bias of a code. It starts with a code with some bias and it improves it. So and makes it and let's say order epsilon square biased code. And so now if you want to get a code which has very good bias, you start off with a code that has some moderate bias. Like you can take one of these codes, except you instantiate it with epsilon being 0.1. So the rate is just a constant. And then you apply this transformation that reduces the rate of the code, but improves the bias. And reduces the rate of the code and improves the bias, and it keeps doing this. And it does it in a way that's that has some trade-off between how much the bias improved and how much the rate went down. And right, so the Rosenman-Wigderson construction itself does not end up giving order epsilon square. In fact, it doesn't even give order epsilon cube. It gives order epsilon to the 4 behavior. But this is the starting construction which Amnon then took and added a lot of clever ideas. Good. So I will just tell you what this transformation is, and maybe I will hint as to how you get the epsilon to the 4 rate behavior from this. So the transformation is as follows. So we have a code C, which is epsilon biased. So we're going to write, so it's also linear, by the way, right? Linear. And now we're going to, the bits of the new code are going to be sums of bits of the old code. We have n coordinates here. And what we're going to do is we're going to pick certain pairs of these and take their parity. So impose a graph G on 1 to 3 up to n. Maybe I should have drawn it like this. So this is G, an expander, D regular with n vertices. And the new code C tilde is xi plus xj for each ij in the edge where x1 up to xn is in the code. So take a code word and take certain pairs of bits from there and add them up. This new code is going to be a subset of f2 to the nd over 2, because that's the number of edges. For each edge, you now have a new bit, which is the parity of the 2 bits written on the vertices. We took a code word, we wrote out all the bits on the vertices, and we took parities. And the claim is if the string x1 up to xn is nearly 50-50 balanced, then this string is even more close to 50-50 balanced. If E was the complete graph, this is true. Why? Yeah, it's right. If it was epsilon balanced, then this would be epsilon square balanced. And that is just because the parity of 2 bits which are half minus epsilon biased is half minus epsilon square biased. Okay. But so the fact here is that this also applies when the graph is an expander, it still holds. So then if lambda is the eigenvalue. If G is a lambda expanded, then C tilde is epsilon square plus lambda. So is lambda between 0 and 1 or lambda between 0 and D? Let's say lambda between 0 and D. So lambda over D biased. Okay, and the proof is a one-line application of the expander mixing lemma. So I will just do that and then I will wrap up. Or maybe I should leave it as an exercise. I leave it as an exercise. I mean, with this, yeah, I leave that as an exercise. So good. So the way to make codes out of this recursively is so start with code of C0 of rate 0.1 and bias, so I call this R0, right? R0 being 0.1 and bias epsilon 0, which is something like 0.1. So we start with some particular code and produce new codes. Ci plus 1 is produced from Ci, right? So it's Ci, from Ci. Ci with epsilon I plus 1 square, no, epsilon I plus 1 equal to epsilon I square plus this lambda I over di. And then what happens to the rate? And the rate Ri plus 1 is the old rate divided by, well, if the original code had length n, the new code has length about n times d, so it got lost, we lost a factor d. Okay, now how do we set this up? So we'll make lambda I over di the same as epsilon I square, so that, so we set di equal to, I guess, epsilon I to the 4, and lambda I will be epsilon I square. That's because we can get eigenvalues being square root of the degree. And then this whole thing becomes epsilon I, is this wrong? Oh, I know. Wait. Lambda is a big number. This is 1 over epsilon I to the 4, yes. And then this is the square root of that, which is 1 over epsilon I square. And so this whole thing is epsilon I square. And good. And this becomes, yeah, so this is order of epsilon I square. And this is Ri times epsilon I to the 4. So the epsilon i's keep squaring as you keep going. And so the final rate is basically dominated by the very last epsilon I that you multiply by. So that's the rate that, so that is the epsilon I, which will, oh, sorry, what I mean is we keep squaring and the very last, you want at the end to get an epsilon by a set. So we keep doing this until we get the final epsilon to be our epsilon, right? So do this till epsilon t equals epsilon. And that epsilon is going to be the dominant factor on this rate. So in the rate, final rate, RT, which is R0 times epsilon 1 to the 4 times epsilon 2 to the 4, up till epsilon t to the 4. This is about just epsilon t to the 4. Because, yeah, they just kept, yeah, because of the way things work. And that's the rate that we got, which is epsilon. And so this gave a construction. So the main ingredient of Amnon's construction of, yes, so there's many ideas, but the main idea is to get a better bias amplifying transformation. One example of such a thing is that gets started is not to just take two edges, not just take two adjacent vertices in this graph, but to take a walk of length t in this graph. And that also does bias amplification much better than a single step. And then to de-randomize that walk using ideas from the zigzag product and things like this. And yeah, so with some cleverness, and there are a few details, but not too many, it leads to codes with this behavior. I think, yeah, let's see. I mean, a big open question from the explicit side is to get codes matching the Gilbert-Varlamov bound for all settings of delta. This is, I think, a really great pseudo-anonymous question. Another really good question is to resolve the gap between epsilon square and epsilon square log 1 over epsilon in the existence result for codes around delta being half minus epsilon. And of course, the full trade-off between rate versus distance in all settings of that. So there are lots of basic open questions, especially about binary codes. For codes over large alphabets, everything has been basically resolved, and yeah, more gets resolved every day. But in binary codes, we've been sort of completely, I mean, prior to this result, there was nothing that had happened for decades. And yeah, and so, but there's still many questions that could potentially be solved. Okay, great, thanks. Yeah. Right, good. That is the same proof. Yes, the fact that degree grows lower than naively, that's the crux of it. And yes, what you said about the relationship between degree and eigenvalues is yeah. Yeah, the trace power, which is basically this proof, right? Yeah, right. Yeah, right.